Hello everyone. Today we are going to talk about the chapter 6, Astronomical Instruments. We'll primarily focus on is the telescope. We already talked about in previous chapters how important is the light of the star. We basically gather all the information from the light the star emitted. And we also talked about by analyze the starlight, we can get the temperature, the chemical composition, as well as how fast the star moves. And in this chapter, we'll talk about what kind of instrument we can collect as much starlight as possible. In this picture, you can see this is the James Webb Space Telescope, which launched in December 25th of 2021. Is so far the largest space telescope humanity has deployed into the space. And the small image I show here is James Webb's image. You can see by using James Webb Space Telescope, we are able to see a lot of details of this nebula. So what is a telescope? What is the function of a telescope? A telescope collects the faint light from astronomical sources like stars and brings it to a focus. So there is a different optics for the telescope. Let's look at what type of optics can perform the function of telescope. You can see here I'm holding a lens, and which we call convex lens, because that is transparent, and you can see it's thinner on the edge and thicker at the middle. Now you can see from a different angle. Now let's take a look how the convex lens can do to the light. You can see here is a light rays, right? You can see they're pretty much like parallel. But if you put a convex lens in front, it can actually focus the light. Therefore, in order to focus the light, we can actually use convex lens. You can see I have this mirror. One side is concave, and one side is a flat mirror, and the third side is we call the convex mirror, right? So this side is concave, and this side is convex, and the third side is flat. Now let's look at how the mirror with different shape can do with the light rays. You can see here if we put what we call concave mirror, the curved down side, you can see it can focus the light. Again, you can see it can focus light. It can bring the light into the focus. So that is exactly what we need for the telescope. Now let's actually use our convex lens, which is focus light. Let's look at how it can form image. So this is a convex lens. And you can see this is a light box, actually emit light of this cross shape, right? So now what I'm going to do is I'm going to put the convex lens in front of a light box to see if it can form an image on the wall. You can see now you have to adjust a little bit of the focus, and we can see something on the wall, but gradually you are able to see the image, the clear image. Now you can see here is a clear image, right? Now let's take a look at a concave mirror. So concave mirror is one side is curved in. We're going to use the side curved in to reflect the light. Remember, the mirror is actually reflect light, so therefore the image and their light source will be in the same way or the same side. You can see here after some adjustment, we can get a better image formed by concave mirror. Therefore, you can see for us to perform the function of telescope, we can either use convex lens, the one that is transparent to focus the light to bring and to form an image, or we can use what we call the concave mirror, and sometimes we call reflector to focus light to form an image. So now we actually have two choices. We actually also have two big category of telescopes. That one big category we call reflector, that's actually uses the lens. And another category we call reflector, which actually uses mirror. And if you see the one with a longer tube, that is actually reflector, use a lens to focus the light. But if the one you see like this one, it is actually wider, but the tube is shorter, this is actually reflector, which use mirror to bring the light to focus. Because the reflector or the mirror reflects the light, if you put your head in front of a tube, you will block to see the focus or image formed by the mirror. Your head will block most of the incoming starlight. So therefore, for the ease to observe the image, we actually use another mirror to kind of redirect the image to the side. So this way you can see the image formed by reflector from the side. So now we have two choices. Let's think about for the modern research purpose telescope, which one you think is better? Is a reflector the one use mirror, or the refractor the one use a lens? Actually, the most large telescope are reflectors. Let's take a look at why people or scientists actually choose a mirror rather than the lens. You can see if they use a lens, it can be pretty heavy, especially if you manufacture the lens to a much larger size. And the mirror is actually lighter, right? If you compare them. Mirror is lighter and lens is heavier. And if you want to support the lens, because the light need to go through, the lens can only support on the very thin edge. So that is the only way you can hold the lens. You cannot block the light by support from one surface. And when you have to polish both sides of the lens to make sure it's perfect polished for the light to go through. However, if you look at mirror actually, we already talked about, is actually lighter than the lens, and it only need to polish one side, and therefore you can build a structure to support a mirror from the back. Manufacturally, it's more easier because the light will only need to reflect on one surface, don't need to use the other surface. And the other drawback of the lens, we call it chromatic aberration. So you can see from this demonstration, when you use a transparent media to actually let the lens go through, you can look at this. It not only bent the light, but it is also split the light into its different color. So therefore, if you use lens, you will run into a problem that you're gonna have different line be split out, so it will be very hard to have a very sharp image. And this phenomena we call it chromatic aberration. Therefore, in summary, that is why modern research uses the telescope, especially the very large telescope. They are all reflectors. The reflectors are mirror easier to manufacture and easier to support. And light does not have to pass through the glass of the mirror. Therefore, we only need to polish one side. And also the mirror does not subject to chromatic aberration, and which is a problem of the lens, which basically split light into different colored component. Now let's look at how the telescope today looks like. And let's look at what is the most important function of the telescope. Remember, we use telescope to focus the light to form an image. The most important function of the telescope is that we want to see more details. If you only see a blurb of light, you cannot tell if it's a star or galaxy. You cannot even tell if it's one star, two star, or multiple star or star cluster together. So therefore, the resolution of the telescope represents the smallest feature can be distinguished. Is the most important property of the telescope. You can think about the better resolution of the telescope, the better the telescope. So therefore, we can see much details. This resolution, or sometimes we call it the smaller the feature or smallest angular separation we can distinguish, is actually proportional to the wavelength and inversely proportional to the size. The size here we use a d, or the diameter of the telescope, to represent. Remember, in this formula, we actually need to have a smaller angle, which represents the smallest feature that can be distinguished. Let's take a look at this mathematical formula. And here you can see we have this angle here. So you can imagine if we have a longer wavelength, what we have? We'll have large angle, right? That means the telescope will have poor resolution because smallest angle it can distinguish is actually larger. And if we only focus on the optical telescope, the telescope that look at the visible light, there's not a lot of things we can do with the wavelengths because it's whatever the starlight bring the wavelengths then we need to observe. If we have nothing to do, have little things we can do with the wavelengths, the only thing we can do is try to manipulate the size of the telescope in order to improve the resolution. So you can see the resolution, the smallest angle, the angle is inversely proportional to the size. So therefore, if we increase the size, what happens? We actually decrease the angle. That means now the telescope can see even smaller angular features, smaller feature. So you can see if you take a look at the picture here, the modern telescope actually use much larger mirrors. For you to have a sense of a scale, this is a human at the same scale, and this is tennis court and the basketball court at the same scale. You can see in order to have better resolution, we actually start to build larger and a larger telescope. You can see the refractor, when you get it too large, the lens actually have a problem, it become too heavy. So therefore you can see later on we all use mirrors rather than lens. And then you can see as the time goes by and to more and more recent mirrors, and we actually build larger and larger. And you can imagine to build one single piece of large mirror, it's become much more difficult, because first of all you have to have a factory to build a mirror, and then second of all you have to build a observatory to put those mirror, and also you're gonna have to arrange a transportation to transport those mirrors into the observatory. So this is very difficult. So people actually found a good solution is that instead of using one single mirror, we can build our relatively smaller mirror and then put them together to let them collecting the light together as if they are from the single mirror. And so you can see later on, the one that they actually planned, those are, instead of one mirrors, is a lot of mirrors together, working together, so to collect the light as if they are function as a one single mirror. So you can see the reason the astronomer like large mirrors or the large size of the telescope is because the larger the size, the better the resolution, the smaller the feature we can distinguish from the object. And another information I want you to take a look at and get from this image is look at the site, the location of the telescope, to look at what are some popular sites. You can see that some popular sites for the later telescopes. You can see Hawaii, right? Hawaii is a popular site. And other than Hawaii, we have like Chile. You can see a couple of larger telescope, and here is several, even for several large scope that is in planning stage. They were in the side of Chile, right? So therefore, you can see from the location, you cannot just put those big telescope like randomly in the center of the city or in a random location. And the reason they select this special location is because the site for an astronomical observatory, we need to have a clear weather. You know that if it's cloudy, you cannot really see any star. And we need a dark sky. So that means it better in a remote area away from the big cities, because big city or the town will have light pollution. So you can see a lot of telescope is actually put on the Hawaii, the island of Hawaii, because it's far away from the big city, and it needs to have lower water vapor. That means lower humidity, because water vapor will also interfere with the light ray and go through the atmosphere. And so the reason why they choose Chile, because first, Chile, the location of the big observatory, they are far from big cities, no light pollution, and also it's actually have a high elevation. And you can see most of the observatory are on the top of a mountain. And why? Let's take a look at how atmosphere can affect the starlight goes through it. You may still remember the song Twinkle Twinkle Little Star. When we observe the starlight from the earth, it looks like those starlights are twinkling, and we call this is actually the atmospheric turbulence. If you look at the starlight above the atmosphere of the Earth's surface, those stars, they won't twinkling. This is because when the starlight goes through Earth's atmosphere, the light will interact like something goes through it or bumped by the air molecule. So therefore, the starlight actually goes through curved path a little bit. So from the observer, it looks like it is twinkling. So therefore, another requirement of the location or the site of the telescope is that if it can subject to less amount atmospheric turbulence, that will be a better site. And if you imagine, if you put a telescope on the top of the mountain, on the mountain there is less air above the mountain compared to the sea level. Therefore, that the observation will subject to less atmospheric turbulence. So that is a better solution. Of course, the best solution to get rid of atmospheric turbulence 100% is to send the telescope into space. And you can see this group of telescopes, although they all have much smaller mirrors, but a lot of them can actually form a very crystal clear image. If you still remember the image I showed you from the James Webb telescope, it is because all this group of telescope is actually orbiting around the Earth. They actually perform the observation above the Earth's atmosphere. None of them actually subject to this atmospheric turbulence effects. So therefore, there's a limit how much we can do on the ground. Therefore, in order to get more crystal clear image, we want to send telescope into space. Although it is the best solution, but it's usually very, very expensive to send telescope into space. Therefore, we actually use some other techniques. We still keeping using the telescope on the ground, but we use some other techniques to kind of correct the effects from the air turbulence. And in terms of how large telescope we can send into space, it also depends on how large the rocket ship can bring. So you can see the Hubble Space Telescope already provide us with a lot of very good image, and but it's basically the larger size single mirrors that can fit into a space shuttle. And for James Webb Space Telescope, you can see instead use one mirror, it's actually use a lot of mirrors. So when it was launched, it's actually folded to a smaller volume so it can fit into a space shuttle or space craft. And when it is in the correct location in the space, then it unfolds these mirrors. So you can see it's actually have a large, overall speaking, the larger size of combined mirror than the Hubble Space Telescope. Other than the visible light, we already talked about the stars, especially very hot stars. They also emit other type of electromagnetic radiation. For example, they emit radio wave, they emit infrared radiation, as well as X-ray and gamma ray. So therefore, if we only use telescope to look at the visible light range, sometimes we call it the optical telescope, we'll only get very small amount of information that can only bring with the visible light. We're actually missing a lot of other important information of the star, which bring in terms of other types of electromagnetic radiation. So therefore, to gather more radiation from a star or to extract the information the star emit not only the visible light, we actually also build what we call radio telescope. The radio telescope is a function is actually collecting the radio wave emitted by the celestial object. For example, the stars also emit a radio wave, and there's also some nebula or some object in the space actually have very low temperature. They do not emit visible light, but they still emit radio wave. So therefore, this is only can be detected, or their property can only be studied by the radio telescope. So how is a radio telescope looks like? Radio telescope, if you look at the overall structure and appearance, it looks like very close to the dish which used to receive the television or the radio station signals. So the radio signal emitted by the star can be collected by the radio telescope. It's a large curved metal dish to collect the radio wave from the space. And it is actually easier to make a radio telescope or radio dish very big because the radio wave actually have a longer wavelength. It is insensitive to the imperfection on the dish. And you can see you don't really even need to build a dome for the radio dish. And let's take a look. You can see this radio telescope. This example is here is the largest radio telescope can rotate to focus on one part of the space. And the diameter of this dish is about 100 meters. And if you compare to the telescope, the optical telescope, you can see the diameter, I would like to say most are currently in use, the telescope is less than 10 meter in diameter. So radio telescope can make it very large. However, there's also a disadvantage of radio telescope or radio observation. Because when we talk about the resolution of a telescope, the radio wave actually has the longest wavelength among all the electromagnetic radiation. Due to the longer wavelength of radio wave, the resolution is very poor. So therefore, in order to compensate this longer wavelength, we have to make radio telescope very large in order to make the resolution better in a range comparable to the optical telescope. And so that is, you can imagine the problem to make a dish very large. You can see this dish is already 100 meters across. You have to build a very strong structure to support a dish. But a human being is actually very smart. And if it's too heavy for a man-made structure to support, let's just go ahead to find some natural structure to support the dish. So you can see this is a radio dish or radio telescope with a diameter of 500 meters. And you probably know there are some mountain top, they actually have this concaved shape. So instead of build a man-made structure to entirely support a telescope, we can build a telescope on top of a mountain. Let the mountain help to support the entire structure. But the drawback for the radio telescope built on top of a mountain directly is that this radio telescope cannot focus on one object because the object seems to moving across the sky during the night. It cannot be changed direction. And so far, 500 meters across is the largest radio dish we can build on the Earth. But human being or astronomer or scientist won't stop try to find a solution to get a better resolution of the radio telescope. And they actually found that similar as the optical telescope we're talking about, we can build several mirrors and put them together to let them work together as one big mirror. We have something actually for a telescope. We call it interferometer. That is, we built a lot of radio dish or radio telescopes, like link them electronically, like combine the data or the information received from them. And so we can actually build a lot of radio dish, radio telescope to let them working together. And the resolution of this interferometer depends on the separation of telescope. If that is the case, you can imagine this basically has no limits on how large the radio interferometer we can build on the Earth. You can see that as long as we put a lot of radio dish very far away from each other, we can basically virtually increase the size of radio telescope, therefore improve the resolution of radio telescope. And one of famous interferometry is we call is event horizon radio telescope. That is actually not one local interferometry, and it actually have like the array of the radio dish from all across the globe. There are radio dish in North American, radio dish in South American, even radio dish arrays, a group of radio telescope in the South Pole, as well as in Europe. You can see all these radio telescopes working together, their separation, you can see, is almost the diameter of the Earth's globe. You can imagine this interferometer were able to observe a very, very, very small object. Actually, the New Horizon telescope is the telescope that give us the first image of a black hole. So black hole, it's a very, very, very small object, and it does not emit light by itself, but fortunately, it actually have the light orbiting kind of around it. So this way, by the accretion disk of the black hole, we know it's actually a black hole. But because it's very, very small, so we really need something with a very good resolution. So that is actually able to achieve by let the telescope or the radio telescope actually working together across the different location on the Earth. And in future, if we want to achieve even better resolution of a radio telescope, we can even increase the separations of radio telescopes. For example, we can put one telescope ray on the Earth, and we can put another radio telescope array on the Moon, or in future on the Mars. So we'll let them do observation at the same time, combine data from them. So this way, there's basically no limits of how large interferometer we can build. And most importantly, the observation of radio telescope is actually bring us to an entire different frequency. We can get totally different information from what we observe from a visible light. And there's actually a lot of objects in the space. They are actually very low temperature. They only emit radio waves. So therefore, in order to detect the property of this object, the only choice we have is a radio telescope. Some example of extremely low temperature objects, such as the cloud dark nebula, and which actually is a site or for a lot of star formation or starbursts. Other than the visible light and the radio wave, there are also other type of electromagnetic radiation actually emit by the star. Remember when we talk about emission of the star basically emit all types of wave. However, if you still remember, we talked previously that only the atmosphere of the Earth only open two windows. One we call this optical window, so only the visible light can go all the way reach the ground. Other we call this radio window, so there's only radio wave can go all the way through atmosphere and reach the ground. So therefore, we built radio telescope on the ground and we built optical telescope on the ground. If we want to collect, for example, the X-ray or gamma ray or infrared radiation that from the starlight to look at the information bring with those radiation. Unfortunately, none of this radiation can reach the surface of the Earth. Therefore, we're gonna have to do the observation outside Earth's atmosphere. So for infrared, it can penetrate atmosphere a little bit more than the rest. So therefore, you can see we can actually have Sophia, which is a telescope on board an airplane, which can go a higher elevation. It can observe some of infrared radiation and function as an infrared telescope. Other than the plane board telescope, we actually have James Webb Space Telescope. It's also infrared telescope. We have also other space-based telescope actually focus on the infrared radiation. And I want to explain a little bit of why we have so many infrared telescope and in the space. You may have heard about the fact that the universe is expanding. So that means a lot of galaxies are actually moving away from us. If you remember what we learned about Doppler effects, when the object is moving away from us, it will experience what we call the red shift. So the light we observe is actually become longer and longer. If it's moving very fast away from us, the light it emits and when we observe will all the way stretch to the infrared region, which have even longer wavelengths. So therefore, James Webb Telescope as an infrared telescope are able to detect very distant objects from the Earth since they are all move very fast away from us. So most of light they emit when we observe from near close to the Earth, it is already being stretched all the way into the infrared wave due to its speed. And other very famous space telescope is like Hubble Space Telescope. You can see Hubble Space Telescope is operate in the visible range. We already talked about the reason we need the space-based optical telescope. It's because although we can build a lot of very large telescope on the ground, however, all the starlight were subject to the atmospheric turbulence. So therefore, by putting telescope into space, optical telescope, we're able to get better resolution. We're able to get a crystal clear image from the stars. And for the X-ray and the gamma ray radiation emit from the star, bring with starlight, unfortunately, they won't able to reach the surface of the Earth, which is a good thing because we don't need to worry about this dangerous radiation can cause the health problem for human body. But in terms of the astronomical observation, that means we have to send the observatory or the telescope to observe X-ray and gamma ray into the space. And if you look at the radio range, there are actually no radio telescope actually in the space. Can you think about why? Remember, we talked about the radio wave due to its extremely long wavelength. It can go around the clouds. So you sit inside the classroom, you sit inside your home, you can still receive your cell phone signal, right? So therefore, there's no need for us to place this heavy metal dish into the space because the radio wave can go around the clouds without any problem. And even for other type of the space-based telescope, those telescopes are actually not far away from the Earth. So they basically all almost all of them in what we call the near Earth orbit. Remember the reason Hubble Space Telescope or similar space telescope can get better resolution image of the celestial object is not because they are closer to stars. They're still very close to Earth, so they are still far away from the star. The primary reason is because they actually orbit above Earth's atmosphere, so it's not subject to the atmospheric blurring effects of the starlight before it reaches the telescope. That is all what I need to cover for Chapter 6. In Chapter 6, we first talk about the basic structure of telescope. We basically use convex lens or concave mirror to build a telescope to bring light into focus and form image. Then we talked about the modern telescope and why we need to have a very large mirrors for modern telescope and the best site location to put those modern telescope. And then we talk about the radio astronomy, how the radio telescope looks like, and how we can use interferometer to increase the effect size of radio telescope for us to see more detail. Finally, we talk about observation outside Earth's atmosphere, why we need space-based telescope for us to observe the electromagnetic radiation across the whole range.